So if we substitute that back in here, we get that when k is not equal to u, we end up with a 0 term, and when k is equal to u, we get a, substitute u for the subscript here, of L minus 2 times this derivative, which becomes, as we've seen, 1. So now we have a value for the partial derivative of the weighted input at neuron V with respect to our weight, and we can substitute that term back in here, which gives us an expression for the partial derivative of the activation at neuron V. So this is equal to the derivative of our activation with respect to the weighted input multiplied by AU, the activation at neuron U at layer L minus 2. So now going up the chain, we already found an expression for this partial derivative, which we have here. We can substitute that in. That is this expression right here. If we substitute that in, we get that when j is equal to v, that is DAV with respect to the weighted input multiplied by the activation at neuron U at layer L minus 2. This is when j is equal to v and it's 0 otherwise. And then we backtrack further and we get that the partial derivative of the weighted input at neuron I at the output layer with respect to our weight, it was equal to this summation, and we see here that when j is equal to v, we get a non-zero term out of the summation. When j is not equal to v, this just becomes 0 as we're substituting this derivative, which we found here, into our summation. And so when j is not equal to v, we just get 0 here. The only term we're left with here is this. So now that we have an expression for the partial derivative of the activation at the jth neuron with respect to our weight, let's backtrack further and substitute that into the partial derivative of the ith neuron at the output layer. And so we have this part right here, and we'd like to substitute it back here. And we see that when j is equal to v, we get a non-zero term, and when j is not equal to v, we get a 0 term. So that eliminates the summation because only one term in the summation becomes non-zero. So when j is equal to v, we get w, substitute v for j, vi at layer L, output layer, and then we substitute this expression, which we derived here, into this partial derivative. And then we end up with the derivative of the activation of the v neuron at layer L minus 1 with respect to the weighted input at said neuron times the activation at the u neuron of layer L minus 2. And then we can go back to our original partial derivative and substitute this expression, which we found here, into the outermost derivative. And then we end up with the partial derivative of c with respect to an arbitrary weight from a neuron u to neuron v in layer L minus 1. This is equal to the sum as I goes from 1 to n of the partial derivative of c with respect to the activation at neuron I at the output layer multiplied by the derivative of this activation with respect to its weighted input at neuron I in layer L multiplied by this, which is the weight going from neuron V to some arbitrary neuron I in the output layer multiplied by the derivative of the activation of neuron V in the previous layer with respect to its weighted input multiplied by the activation of the youth neuron at layer L minus 2. So now we have a generic expression for the derivative of the cost function with respect to a weight for an edge going from layer L minus 2 to layer L minus 1. Previously, we found the partial derivative of the cost function with respect to the weight of an edge going from layer L minus 1 to the output layer L. So let's summarize our results.